but not, sorry, and it should be something else here. 0 minus 8, 16. All right, so let's see. So that now let's do, so remember, I'm not allowed to scale the second row, so I have to leave it this way. So the next thing I can do is do, so if I take 2 times, or sorry, half of row 2 and add it to row 3, it'll get rid of that minus 8. So take row 3, replace it by 1/2 row 2 plus row 3. Okay, so let's see right here, blue. So I'm gonna make, so this is my 1/2. So that's what's gonna go here. So the opposite of the opposite sign of that number. So it's gonna be minus 1/2. So and then you get this matrix: 1, 4, minus 3, 0, 16, minus 1, 0, 0, and then 15.5. So now this is L and this is U. So A is going to equal 1, 0, 0, minus 2, 1, 0, 3, minus 1/2, 1, times 1, 4, minus 3, 0, 16, minus 1. Like this, okay? And yeah, so is this procedure is how you get the LU, all right? The other way you could have done it as well, which is I think row 2 should be different because I switched the sign. Which sign? Are you talking about the 16? The minus 1 or? So hold on, let's see. Oh no, sorry. So you mean like okay? Yeah, this is the final answer. Oh, you mean like did I add it wrong? No, because I have notes right here. I copied it wrong. This is what really happened. So this should be fine. The matrix is fine. Okay. Okay. So what was I gonna say? Yeah. So okay. So this is one way to get LU. The other way, which you will never want to do ever, is do this way, right? So take the RREF, write out the elementary matrices. Once you write out the elementary matrices, you get this thing, and then take the inverse of all those, and then take the product, which is something you wouldn't want to do. So this way is much faster. So do this way. All right. So I think that finishes off, and let me just give you the challenge question that I couldn't give you last time. So let A and B, I guess, be square matrices, right? And suppose that A times B is equal to the identity. Prove that A inverse exists, or in other words, A is invertible, and that A what was it? So you want to do that. So I think what we want is equals, and, oh yeah, and then yeah, this right there. There we go. Let me see. Hold on. I'm pretty sure this is the correct statements. So Oh, sorry. Sorry. So, yeah. And that's B is equal to A inverse, okay? So remember, so I didn't say, so again, you can't just multiply both sides by A inverse. I never said A was invertible. You first have to show that, and then once you show that, you get that result, right? So yeah, you can use, and then the way you can do this is use elementary matrices, or you can use the next chapter that we're going to probably discuss to show this as well. And if you use the tools from next chapter, this actually becomes very trivial. All right, so now let's move on to the next chapter. That ends the chapter, all the stuff we need for chapter 2. But first, let me just make some notes. So numerical notes. So in terms of LU, okay. So LU takes LU factorization takes 2/3 n cubed computations.
So have you gotten any more information on the test?
So if you find LU, the number
I
of
got some
computations
information
is
on the test.
this, right?
Like
If you try to find n
how
inverse,
it's going.
it takes
yeah, so
2 n cubed. So they're
My
about the
group me's
same,
been going,
right?
and it's kind of like they're all kind. It seems like we're all not quite sure on how it is.
Let's see.
yeah, well, I got an email from Hanson saying
2.
that log on to
So when you solve a system,
our
right?
regular Zoom with the camera.
You usually solve
10
these
minutes
equations for the LU.
with camera on 10 minutes before exam starts. Log on to Blackboard and click the
So this
matching link
takes
there.
about
Same as homework
2
link.
to the n
Find
squared
exam 1 spring
computations.
2021 link under assignments tab.
However,
Complete
and
exam,
also
make sure
if you
have
find the
answers selected
inverse
for each question.
and doing this, because this solves
So
the
it's
equation
just like
too,
how our physics
also
was.
takes
Sort of, I think.
2n squared, but is less accurate.
You have from 7 p.m. to
And now
8:15
I don't mean it's less
promptly.
accurate
No time
like as in the
extensions will be
method is
permitted.
not
Good luck.
like you get different numbers. I
So
mean
it's
literally
just a monitoring
implementing it into a
Zoom.
computer.
I don't know if that's
you get
just
round-off. You get round-off error.
Well, I think that's how ours.
Hanson?
LU doesn't have that much error, so you
I
get
think that's us too.
a lot
I
more
think that's for
accurate
everyone.
than doing this.
Yeah, because people were
But it's
talking
less
about
accurate.
let's see. So someone's like, so will the exam just open up at 5 on
LU.
mastering? And at first I'm like, what? And then someone said,
And then yeah, so those are the only two notes on it. So I mean, these are the advantages of the
and the guy
of
says,
LU.
it says we
as
should
opposed to trying to find
we
A
should
inverse.
to get on Zoom.
Okay,
That
so
mandatory
but yeah,
just
let's move
if we
on.
have any questions like
So chapter
2
3.
hours before the test on
So this
Zoom. I
is
don't think
called
that's right.
determinant. Okay.
I think it'd be more like the 10
there
minutes thing
are
would be enough for any type of instructions.
many useful.
And he said she never said that it was mandatory, but I'm 90% sure it is. They want you to get on Zoom on your phone and prop it up.
And I'll tell you what that means.
I don't know why.
Hanson's thing just says.
That's end of
just hop on the
week
Zoom
3.
call
So this
with the
stuff now
camera
is
on.
going to be week 4 stuff.
That's probably what I'm gonna do.
I'll tell you what that means
about
in a second. But let's first
in my
talk
group
about
saying
what it
some
means
people have to have their phones on or
pictorially,
whatever.
I guess. What it means like in geometry.
She hasn't sent an email today.
So but first, let us
and we have the printout sheet can have that when you print out.
What it means.
Yeah, it has. Remember that number we were looking at last night? That
it has that number.
Yeah.
It's like okay.
Yeah, for like the A36 steel.
R2.
It has that number
Right,
on it.
so,
it's like 29
all right,
whatever.
so
29 KSI.
let's go over here. So suppose.
Should I ask in the group me if like?
I've got it.
She posted her. My teacher posted her
2
review video thing.
Let's
the
say
video of her
B1
going over the review.
And B2.
Yeah.
I'm gonna watch that right now.
Now let's plot these vectors. In standard position.
Alright, so it is through Zoom. I just need to figure out if I'm doing it through my phone or not, I guess.
So I'm
I
gonna
was like, if it
call
was to my phone, it's gonna be
this
even
guy.
easier
This guy
for
would
me.
be the
I'm
red
gonna
one,
like put it
and this guy.
at a weird angle or something.
So let's say this.
I don't know.
Yeah, but then we're like, are they gonna want us to angle it down on our work? Are they gonna?
Well, a lot of laptops can't do that, so.
And let's say this
Yeah,
one was
because
like
that's what we were saying. Because like,
And how are you supposed to get that angle with your phone? I feel
okay.
like the phone's the
So
worst
we
idea.
have
yeah,
these two.
because we
So
were
that's
like,
B2,
well,
and this is a
if our
B3.
camera's integrated and they tell us to turn
So
the
what
camera
the
around to show our
determinant
screen,
is
then what
it
are we
has
supposed to do
two
for integrated webcams?
interpretations. Well, no, sorry. It has two things that you have to know about this. So
I'm gonna watch
first
this review video and maybe she'll mention it.
is
She
the
probably
determinant
will.
of
If
these
not,
two
hopefully she
vectors.
emails.
All right, well, I'm recording a lecture right now, so I'm getting this full conversation in it by accident. So this is nice.
Alright.
So let's
I
put
don't know
that
how
right
to
there. So
filter out
you do
Discord
the tell
audio.
the head method.
I didn't even know you've been recording lectures.
Yeah, I've been recording it all semester.
Which lectures?
This is linear algebra.
So you see how we get this parallelogram?
Alright, well,
Yeah.
bye.
See ya.
Well, the determinant. So the determinant is the area of these two vectors. Okay? But not just area either. Vectors also, I mean, the determinant also determines an orientation of the area. So it's actually more appropriate to say an oriented volume or area. It will be a volume in higher dimensions, but so you'll see right now that when we complete determinants, you'll see that some of them are going to be negative numbers, and you might ask like, oh well, I thought you said it was area. Well, the sign determines its orientation, right? So like I think in physics you remember the right hand rule. You do like this, and it determines like which way the vector is pointing and all that. Well, it's related to this in some sense. So yeah, so determinant you can think as an oriented volume, okay, of between two vectors in any dimension. Okay. So then yeah. So it's okay. So that's what it means geometrically. Now let's actually dive into how like this stuff is, I guess, how we can compute it and what it means in terms of matrices. So section 3.1. And so the determinant of a matrix. Okay, so let me just okay, so let's give I'm just gonna give like a minute history of it. So basically the determinant, how it arose, it actually arose even before matrices. I mean, you saw it was like in vector stuff right now. It actually, I think, arose around 3rd century China. So the determinant was basically used to do this. If I give you a system of equations, how can I determine if it has a unique solution or not? Well, that's what the determinant tells you. Is it determines whether or not this thing does the system has a unique solution. So then later on, they started to develop the theory a little bit more. So afterwards, I think like Laplace. So there's three definitions that we have. One is the one that we're going to do right here, which is the Laplace expansion or cofactor expansion. Then we have the algebra definition, and I mean like with like groups and stuff like that. So you have permutation groups, and you define it this way. And then last but not least is the coordinate-free definition, meaning if you ever heard of the buzzword manifolds and all that stuff. So you also have a definition in that sense as well. So you'll start to see that. So we won't in this class we'll focus on the first one, the Laplace one. All right. So we need, okay. So in order to define this, we need to first define what the determinant of a 2x2 is, right? So we start by defining the determinant of a 2 by 2 matrix. So definition. So let's say you had a matrix that's a 2 by 2 square. Then the determinant of, let's say I have this form, and it's denoted as either det of A, absolute value of A, you can also say, or I guess they also say triangle of A, is this. So I'm just going to use det of A. And so it'll be A, B, C, D. And basically all you do is multiply the diagonals, like take this diagonal right here, multiply those, and subtract it from these two. All right, multiply it obviously. So it'll be AD minus BC. Okay. All right, so that's the first one. So obviously, it's very, very easy. If I just give you a 2 by 2, literally just do this, and that's the determinant of it. Okay, but now let us discuss the next problem. How do I define a determinant of something bigger than a 2 by 2? Well, this is when we start talking about cofactors, expansions, and minors. Okay, so first let's define two things. So in order to define a determinant of a matrix A when n is greater than or equal to 3, we need to define minors, a minor of a matrix, and a cofactor. Okay, so let us define it, and then let's actually do an example in computing this. So let A be a square n by n matrix, then the minor denoted as Mij of A is of the Aij entry is the determinant of the matrix obtained by deleting the ith row and jth column. Let's see. Okay. And then once you have the minor, the cofactor, so the minor cofactor Cij of the entry Aij is defined as this. So you take Cij, and this is equal to -1 I plus j times the minor of ij. Okay, so all this is like hard to parse, and it might be hard to understand for a first glance, but let's actually reinforce this idea using examples. Honestly, it's not that hard. Once you get like practice, it's like it gets second nature at some point. All right, so let's do an example. So 3.1.1, find the minors and cofactors of also along, I guess, along the first row of, say, this matrix. A, 1, 1, 1, 2, 3, 4, 5, 6, 7. Okay. Okay, so I'm only going to go along this first row since that's what the question said. So solution, first thing you do is, okay, I'm just going to list them out. So I'm going to do M1. I'm going to do the minors first. So M11. M11 is going to be, so let me actually color code it. M11, it will be, I'll start off here, okay? So let me actually take a copy of this because you'll see what I mean by this copy. So take this, and in order to find a minor of this, literally just delete that column and that row, and whatever's left there, take the determinant of that, okay? So this is going to equal, well, what's there? What's 3, 4, 6, and 7. And then we already know how to find the determinant of a 2 by 2. So it's 3 times 7, which is 21, minus 24, which is going to equal minus 3. Perfect. So now 2. Let's do another one. M1, 2. So again, let's paste this over here. So M1, 2. So that refers to the first row, second column element, right? So it's going to be referring to this guy. And then, again, literally just delete that, and whatever's left over, just take the determinant of that. So do 2, 4, 5, 7, which is equal to 14, minus 20 equals 6. And then third, let's say we take, I don't know, like M13. So again, so that refers to the first row, third column elements, okay? So it's this one. So just get rid of that stuff, and just take the determinant of what's left there. So 2, 3, 5, 6, and this is going to equal 12 minus 15 is equal to minus 3. And that's it. So those are the minors. Now let's look at the cofactor, right? Well, since we already have this, finding the cofactor is going to be easy. So let me just take this and like so copy. So let's put that here. Oh, what just happened? Okay, so what is this going to be? So C, so the cofactor 1, 1, right? Well, what's that going to be? Well, it's going to be equal to -1 to the 1 plus 1 power, which is just going to be squared of M11. Well, -1 squared just 1, M11 is -3, so this would be -3. 2. C12 is going to equal to the -1 to the 1 plus 2 power, which is 3. I should have probably changed color. Whatever. It doesn't matter at this point. M12, which is going to be, well, it's going to be -1 times the -6, so it's just going to be 6, -6. And then last is going to be C13, which is going to be -1 of 1 plus to the 1 plus 3 power, which is just 4. M13, which is going to be then just -3. And that's basically how you find these. Yeah. Because it's -1 to the third power, which is -1, and 1, 2 is 6. -1 times 6 is -6. Sorry. Oh shoot! Yeah, you're right. My bad. Okay, yeah, minus 6. Then yeah, then I mean in that case this would be right. So that'd be negative 6 times negative, yeah, so it should just be 6. Yeah, my bad. Yeah, that should be negative 6. Negative 6. Perfect. Yeah, thank you. Okay. How do you determine the power? Just look at this right here. Look. So look at these two numbers. Add them together, and that'll be the power. So 1 plus 1 is 2. 1 plus 3 is 3. 1 plus 4. 1 plus 2 is 3, and then 1 plus 3 is 4. That's how you do it. Yeah. But I'll show you the basically this is how you keep the signs of the determinant, right? I'll show you this checkerboard little thing that you don't ever have to remember this. So I'm showing you the hard way, I guess, first. After this, you probably won't ever have to, I guess, remember all this stuff again. Now, note that for a 4x4 matrix, the minors would be the determinant of a 3x3, right? So I took a 3x3, its minor was a 2x2. So okay, so if I get a 3x3, what do you think I'm gonna have to do? Well, I'm gonna have to take the minors of that thing, right? So you kind of see it's gonna start being very tedious or computationally expensive in that case. So, but we still have to find a definition for it. So basically, what this is that we need to define the 2x2 case first, and then we can define the rest recursively, right? So I don't know, for a 4x4, take the determinant. Well, you'll get its minor, and there will be a 3x3. But for the 3x3, you still have to take its minor. So you see how it's kind of recursive in that way. So this is now the definition of determinant. So let A be a real valued matrix that's square, where let's say n is greater than or equal to 2. Then the determinant is the sum of the entries of the first row okay, I guess it's not really it should be more like the sum of the cofactor. So the sum of the entries of the first row of a that's actually right. Yeah, multiplied by the respective cofactors. So basically, it'll look something like this. So the determinant of A is going to equal, well, you can also denote it this way, is the sum from j equal 1 to n of aij of, sorry, not I, it should be the first row. It should be j of c1j, okay? So, pretty ugly definition, but we'll see that it isn't that bad once we start to like see the pattern. All right, so let us do 2 examples. We're going to do one example just using this definition, and then another one where I can just show you can keep the track of the signs in an easy way. So all right, so let's see example. Yeah, so let's do example 3.12. So find determinant let's say this matrix right here. 0, 2, 1, 3, -1, 2, 4, 0, 1, right? So again, all I have to do is do the exact same thing I did last time, right? We wanted to find the minors, the cofactors, and then at the end is just adding them together by multiplying these entries. So let's do it. So let's find M11, okay? So first entry is 0, so just in your mind, just get rid of the first row, first column. It should just be -1, 2, 0, 1. This should just give me -2. Do M12. So that one just give me 3, 2, 4, 1. Yep. And this will give me -5. And then 3. Just get M13. Find the determinant. That should be 3 minus 1, 4, 0. And that should just give me 4. Okay. So first do this. And then do the cofactor stuff. C11 is going to equal to -1 squared, M11, which is just going to be, so what is that, -2. C12 is going to equal -1 to the cubed, M13, sorry, M12. So it'll be negative times, so it'll be 5. And then 3, C13 is going to equal to -1 to the 4th, M13 is going to equal this, so this would just be 4 in that case. Okay, so now we have everything, right? So at the very last step is to just add them together as with that formula that I gave in the definition. So determinant of A is going to equal, so let me go get this matrix here. So it's going to be the cofactor times that entry. So the first entry was 0, so it's just going to be 0 times -2 plus then the entry that goes right here, which is 2, so it'd be 2 times the 5, and then this 1 times the 4, and then plus yeah, so I guess all in all should be equal to, so should just be 14. Okay. So I guess if you guys took Cal 3, if you do the cross product, you guys should already know how to do this, right? You basically cofactor expand across the first row for the ijk, right? However, notice that here, what is one nice thing that happened with this matrix? Well, at least with the determinant. What was like one thing that was convenient, I guess? Oh, hold on. Y minors of 1 and negative. -2. Why are they? Because I was just copying in this. Hold on. So it'll be, yeah. So it'll be negative. It should be 1 times. Yeah. I don't know why I did that. My bad. So it'd just be -1 times 1, which is -1 minus 0, which would just be -1. So 3 times 3. So that one's fine. 0. So this one's fine too. So it's -4, so it should be +4. So it's fine. That one's fine. Okay, so in that case, then the only thing that changes is this. So that one should just be -1. Yeah, that's fine. So then this is just -1. Yeah, it still gives it the same. But anyway, so what was convenient about this matrix? That there was, I mean, did you see how this one didn't matter at the end? So that's actually something to look at. When we want to take determinant of matrices, we'll see right now, but we want there to be as many zeros as we want, and when we're trying to expand. In Cal 3, you did a 3 by 3, you only expanded the first row, but there's actually a nice thing about this stuff. So it turns out that you can cofactor or Laplace expand. So Laplace expand across any row or column. So it isn't just restricted to expanding across the first row. You can do it along any row in any column. And how do you choose whether or not to be that row or column? Well, you want to choose the one that has the most zeros in that column or row, right? Because you can see that stuff, you'll start getting like cancellations from the 0. So theorem 3.1 determinant of any let's say square matrix can be computed by a cofactor expansion along any row or column. Okay, so you just do the exact same thing that we did there. You just do the minors along the row or the column, right? That's all you do. So, okay, so now let's talk about maybe I guess. Oh, you can't see it. So now let's talk about a shortcut, or I guess more of a, it's not even a mnemonic, but it's just like a shorter way to think of it to shorten your work. So we can use this checkerboard pattern matrix to just keep track of the signs and we don't have to refer to the formula that I gave anymore. Okay, so let me do that and so further. So you can see that. So we can use the checkerboard pattern to determine the sign of the cofactors. And I mean by that, by like this. Key. Like, okay, so where can't you see? Like, is it up here or like down there? So, hold on. Maybe I have to like now do this. would that be fine? Okay, we'll just continue. I guess I'll just the bottom. Okay, perfect. All right, so this will keep track of the sign for us. So now we don't have to like ever do that what we just did again. So example 3.13. Find determinant of, say, a equals 1, 5, 0, 2, 4, negative 1, 0, negative 2, 0. And then I'm going to keep this checkerboard pattern here. So I'm going to make it here. So plus, minus, plus, minus, plus, minus, plus, minus, plus. So now I can now expand along any row and any column. So which one would I want to expand by? So I guess pick which one you would expand around. Which one? Third row. Yeah, the third row, right? Because it has 2 zeros and just exact. So basically, what's going to end up happening is this. So the determinant of a, which is going to be just 1, 5, 0, 2, 4, negative 1. 0, negative 2, 0. Well, I'm going to expand around. So I'm going to do, so this one won't matter because it's just going to be 0 times some determinant. So I don't care about that one, right? And I'm going to keep this sign. Okay, so now the second one for the third column is going to be minus, whereas now it's going to be negative 2 times the determinant of 1, 0, 2, negative 1. So reset. Right, so that's fine. And then for the third one, it's just going to be plus what's going to be 0 times whatever, right? So these are just going to go away. And all you're left with is that now it's going to be 2 times 1, 0, 2, negative 1. And so that determinant of that is just going to be, so it's going to be minus 2. Correct me if I'm wrong, but yeah. So you see the advantage of expanding around along a row or column with the most zeros, right? We don't have to care about those two other determinants. So it cuts down on the our work, you can say. Okay, so I guess since we're running out of time, so let's start the next example. So what about this guy? Let's say a is equal to 2, 0, 0, 0, 0, 3 minus 3, 0, 0, 4, 7, 5, 1, 5, negative 8, 6, 4. All right, so which one? Okay, so now which one would I pick to expand? Which one? Yeah. The first column, right? Yeah. So I'm going to expand around this column. So solution. So again, let's make our checkerboard plus, minus, plus, minus. So the determinant of A is going to be equal to, well, the first one right here is going to have a positive sign, so it's going to be 2 times the determinant of negative 3, 7, negative 8, 0, 5, 6, 0, 1, 4, right? And then all these other ones, as we saw from the last example, are not going to matter, right? So you don't have to expand those. Okay, but now we have this 3 by 3, so now we have to do the expansion again, right? So it's going to be 2 times. So which for the third one, for this one, what am I going to expand around? The first column, right? Again. So it'll be -3 times the determinant of 5, 6, 1, 4, and then these are not going to matter anymore, right? And then also, I guess you can make your checkerboard pattern here. And so all you're left with is 2 times -3 times 4 times 5 is 20 minus 6. Oh, hold on. Do I want to do that? Yeah, I was screwed up. Well. So 20 minus 6 is 14. And this will give me, I don't know, like what, 6 times 10 is what, 60 times 4 is 24, so 84? Yeah, right, okay. So minus 84. Okay, so I guess that pretty much, but notice that this, so imagine if those weren't 0. How hard do you think this would have been? Well, not hard, but like how tiring would have been. It would have been a nightmare, right? So we'll go over that that highlight here next time. But yeah, so that's pretty much it.